So the next speaker is Wael Bahsoun from Loughborough University, and the title of his talk is Linear Response Due to Singularities.
All right, thank you very much. Thanks for the invitation. It's also my first time here in Rio. I'd like to talk about a joint work with Stefano Galatolo and the type of maps that I'm going to consider. They are interval maps. So this is a parameterized family with some epsilon. And here epsilon is bigger than or equal to 0. These maps, they will be piecewise uniformly expanding with a singularity here at some point C in the interval. I'm not going to list conditions on the order of singularities and so on, but instead I'm going to put an explicit example of the type of maps that I consider. So this is T epsilon x equals, I write it in somehow a weird way, but just to see that things add up. Okay. This is for x in 0, 1 over 2. And then I take a reflection of this. Probably I don't need to write the equation of the second branch. All right, so what do we prove? Let me start directly with the theorem instead of history. I start with the theorem. So what we're going to prove is the following, that for any epsilon in some interval 0 to epsilon 0, epsilon 0 sufficiently small, okay. T epsilon admits a unique invariant density and we call this density H epsilon, all right? But what I'd like to stress in this first part of the theorem, that we know that H epsilon is quite regular. So it's in W to 1. This is the new thing. And what else? Well, is the title. Moreover, this epsilon H epsilon is differentiable at epsilon equals to 0. Yeah, well, let's say where? In L1. So in particular, we can write H epsilon equals to H0 plus d epsilon H epsilon at epsilon equals to 0. There's an epsilon here, plus little o of epsilon, and the little o is in the L1 topology. All right, so for those who don't know what linear response means, it really means what I wrote here. So the idea is that you have an initial system or a parameterized family So if you have an initial system and you perturb it, or if you have a parameterized family and you look at the family, at the statistics of the family as the parameter varies, if you see differentiability of the density or the measure in general, then we say that the system has a linear response. And no one said anything, right? And you get this first order approximation, and usually you can write an explicit formula of the derivative here. So basically what you're saying if I know the statistics at epsilon equals to 0, and my system is differentiable, so roughly I know the statistics of nearby systems up to an error O of epsilon. Yeah, so this is usual first order approximation. Pardon me?
What is W21? Similar space?
Yes. So this is the Sobel space W21. Okay? This is what I mean by W21. Is this okay with everyone? All right. Excellent. Yeah, so of course, a natural question, you say, okay, if I see someone giving a talk about something like this, the first question I ask, why the heck would you care about a family like this? Okay. So let me start with some history about this linear response business, and then I come back to saying why we thought of studying this family, and then I give a proof to the theorem. So previous work the first work in this direction was by Wael in 97, where he studied the axiom A systems, and in such a case, if you perturb smoothly in a C1 way, say, then you can show that the SRB measure has a linear response, and there you study the error, for example, in the weak topology. Yeah? A natural thing to do when you are in a hyperbolic setting. So that was the first result for axiom A. Then Dorcopiat, and which year? 2004. This is for some partially hyperbolic systems. And again, he proved the linear response. Of course, this is for certain partially hyperbolic systems. I'd like to mention some work by Guzel and Liverani, and also Butterly and Liverani, where in these two papers, they studied Anosov systems. Nothing new in terms of linear response, but they proved in this case that if you have higher order regularity in your system, you can even prove you can get a higher order approximation. Moreover, the technique that they use in these two papers is basically the technique that I'm going to present here, based on transfer operators. All right, so so far in this smooth setting, if you perturb the system in a smooth way, the situation is okay. You get linear response. So let's come to some not so nice settings where we are in a piecewise setting. So this is all smooth. And now for piecewise. Well, the first bad news came in 2007 by Baladi. And where she reported an example, and she mentions in the paper that this is due to Avila. And the example is way more simple, well, in some sense, to the one I'm presenting there. It's basically a perturbation of the tent map. So let me write it in the same style as the one I wrote there. And something like this. And for this example, she proved the following. There exists a phi in C1 such that phi d mu epsilon, okay, this map here, is not Lipschitz. It's not only that you don't get linear response, but even worse, in the weak topology, you don't get Lipschitz continuity. Okay. All right. Then comes the the famous work of Baladi's Mania in 2008. Here. This is in 2008, where they studied, well, if you look at the picture here, you have something like this. Yeah, this is the tent map. Full tent map. And then you're moving this down a little bit. Okay. So in this paper here, again, they studied the piecewise uniformly expanding map of the interval, unimodal, in the sense that you have a critical point here, but uniformly expanding. And they proved the following result that I summarize. It says that linear response is violated if and only if T epsilon is transversal to the topological class of T0. Okay. So the situation in a piecewise smooth setting is not so good as the situation of smooth systems. And, well, one thing that we thought initially is to do the following. Well, if the situation is bad, try to make it worse, see if it gets better, somehow like this. So what we want to do, we want to see if instead of having just a usual critical point, we want to see what happens if we have a singularity, meaning a blow up in the derivative, as you notice from the equation here. And it seems that the situation gets better. Another motivation for this work is to really start to get ideas on, well, if you are in a piecewise smooth situations, what are the things that you look for so that you get linear response? One criteria here which I try to stress on is that I have H epsilon. For any of these epsilons, it stays in W21. If you want to look at some kind of intuition of what happens, well, here, if you look at the initial system, well, the invariant density is just Lebesgue measure. You have the uniform density. And once you perturb, you get a jump in your density. However, in a situation like the one I drew there, well, you go to 0 in a smooth way. The density goes to 0 in a smooth way because of the singularity. And this is something which is something good to keep in mind, is to stay as regular as possible. And as you will see in the proof, I want even to, I didn't say, for example, I want to be in W11, but I want it to be in W21. And this will be more transparent in my proof. Other motivations, of course, well, if you look at a singularity like this, you think about Lorentz type maps. I'm not going to say anything there because we don't have a result, but it's a first step to start thinking what to do in a situation like a Lorentz-like map. And then more, I gave this talk in front of Liverani, and he told me, well, something like this may give you also ideas about what to do in higher dimension, because solar spaces in higher dimension, they accommodate discontinuities and singularities better than solar spaces in one dimension. So this is something also to keep in mind for future work on linear response. All right. So that's all. This is all what I wanted to say. And now I'm going to present the proof of this theorem. Okay, I wrote it down because I expected someone to ask me about it, and it's not so easy to say. No, but I'm going to say, ask Daniel. Daniel will tell you. All right, so definition. So T epsilon is tangent to the topological class of T0 if there exists tau tilde epsilon, well, tilde, not bar, such that I consider the soup of T epsilon x and T tilde epsilon x. As I remember, this is big O of epsilon square. And there exists a homeomorphism, H, such that, so you have a critical point in, so H of C equals to C, and T epsilon tilde equals to, well, you have a topological conjugacy. So this is T0, and this is composed with H epsilon inverse. Ah, there's no epsilon, sorry. You have epsilon? Okay. I don't remember the. So this is the definition. It's not something easy to check, actually. You agree? To find. Okay. All right. Let me give a proof of this theorem. So I'll keep. What I'm going to do initially, I'm going to assume, let's say, this part. Assume I did this part. I'll do it at the end. And let me show you how you prove linear response with transfer operators in general. It's a very simple thing if you know, if you have a good picture. Okay, so let me say proof like this. And let's say I've shown that H epsilon is in W21. Okay. So in this business, linear response, you need 3 Banach spaces. And my 3 Banach spaces will be well, I will start from the most regular one, W21, and then W11, another regular space, and then L1. I want to differentiate. Well, let's do some calculus. So I want to consider the difference of these two guys, and something to check easily that if you take I forgot, sorry. Definition, the transfer operator, I'll put it here, recall. That, if I define L epsilon, this is defined as follows. So if I take G in L infinity, F in L1, G composed with T epsilon times F. This is the same as G times L epsilon applied to F. This is how you define the transfer operator for a non-singular map. And then you saw in many talks the pointwise formula. You can derive it simply by taking this L infinity function to be an indicator function of a set. You get a pointwise formula. All right, so I defined what I mean by L epsilon. This is the transfer operator. And if I do the following calculation, I see that this is the same as L epsilon minus L0 and apply to H0. Okay? This is a one-line calculation. It's always correct. I didn't do anything here except using the fact that these H epsilon and H0 are fixed points of the corresponding transfer operators. Well, I want to differentiate, so I'll be tempted then to take this guy here and put it on this side. Okay? Well, to do this, I need a spectral gap. Well, first of all, let us observe that this term here is a zero mean. Yeah, if I integrate, this is integral 0. So if I have a spectral gap on W11 is enough for me, then I can write this H epsilon minus H0. I can write it as I minus L epsilon inverse. And this is applied to L epsilon minus L0 applied to H0. Okay? And let us call this equation 1. Okay. So far, I'm not doing anything special. As I told you, this is like basic or like routine steps if you are using transfer operator techniques to obtain a linear response. Okay, so one thing to do, you need a spectral gap on W11. All right, now we want to differentiate. So let us start working with this guy. So I want to consider now L epsilon minus L0. And this is an assumption. Well, you can put this as an assumption, which you can check for your example, that you have a differentiability. You can write this as epsilon times some q. This is the differential of this operator plus little o of epsilon. And here, this little o of epsilon is understood in W11. Yeah, so let me say that this is an assumption that you check that it's satisfied for the examples that you have. Yeah, once you have a formula. Okay. But one thing which I'd like to mention here is, well, once you do a differentiation here, once you do the calculus, if you want to differentiate, to be able to differentiate, so you're doing this d epsilon of L epsilon at epsilon equals to 0. Well, this is applied to H0. You see, there is, once you do a differential in epsilon, for this object here, you're going to get a derivative in x for H0. So this means you're going to lose 1 degree of regularity of your density here. So therefore, I needed, at least for this point, I needed my H0 to be in W21. Okay? So that I know that this guy is in W11. Okay. Well, this is one step. I have this differentiability. I'd like now to apply this to it. Well, to apply this, to get a first order for this term, what I need to know that this operator here is uniformly bounded as an operator on W11. Again, if you look at this guy, this is 0 average. And what I want to do, well, I want to write this in the following way. So I get then epsilon times I minus L epsilon inverse applied to Q plus little o of epsilon. What's the justification here? That I don't only get a spectral gap on W11, but I get a uniform spectral gap in epsilon also. And hereby uniform in epsilon. Okay? So this is justified, this step. And finally, well, the last step, I need to prove the following continuity. I need to show that epsilon I minus L epsilon inverse at Q is continuous at epsilon equals to 0. And this is continuity in L1. Well, many of you are experts in this. Well, what we have, we are in a situation where this is in, Q is in W11. So if I have my continuity of this operator, and so if I have this from W11 to L1, this goes to 0 as epsilon goes to 0. Once I have something like this, which is, again, something that one can check in an example, then spectral theory will tell me, well, stability or Keller-Livrani stability results will tell me that also these resolvents, they are continuous from W11 to L1. Then I get the result. And what I can write finally if I add all these steps. So I call this 1. This is step 2, and 3 and 4. So if I add these together, I get the linear response that I wanted. So I can write H epsilon equals to H0 plus epsilon d epsilon H epsilon plus at epsilon equals to 0 plus little o of epsilon. All right, so this is the proof of linear response. And as I said, this is pretty general. There is nothing special about what I presented here. You need 3 Banach spaces, and you need to verify these 4 steps. And the crucial thing is to show the following, that you have a uniform spectral gap. And let us see what was the trick here. All right. Well, for those of you who know the Lorentz 1D map, Lorentz 1D maps, and how you prove, say, you want to study, say, the existence of the invariant density for a Lorentz 1D map, you have 2 options. Well, it depends what you want to do. One option is to induce. If you like to induce, you have to stay away from the singularity and get something nice, piecewise uniformly expanding, and C2, and then you get the result for your induced map, and you come back to the original system. Another way of doing this, which I like, well, I don't mind the other one, no offense, but I prefer transfer operators is to use a result by Keller, who in 85 introduced a space which is called the generalized bounded variation space. And such maps, the ones that I have here, they fit in the space that Keller introduced. They are good for such bad singularities. And you can get a spectral gap there. But the point is that that is a BV type space, BV space. And what I want to do, I want my densities to be more regular than this. I want them to be in W to 1. Yeah? Why? Because I need 3 Banach spaces. I want to differentiate and get to the second Banach space. And moreover, I want to be able to verify this guy here. Okay, so what do we do? The problem with, okay, let me say something about Keller space. Keller space avoids this, what we call here, what's the loss here? The loss here is that we don't have what we call bounded distortion, usual bounded distortion, yeah, for maps like this. Well, Keller's idea is, well, you have, if you have bad bounded distortion, maybe this guy is not so bad, okay? You look at the regularity of this guy, and you study the p-variation, say, of this. And if this is fine, then you can prove a spectral gap in his space. So you avoid, taking this usual T double prime over T prime square. Yeah, the usual distortion thing, which you don't have in this situation. Let us see how we avoid all this stuff. And let us do first a Soto-York inequality in W11. Okay. And this is the key idea, actually, in the whole thing that I have said. It's very simple, and it was surprising to us that we could recover linear response for such systems just by adding a cusp here. And with the systems that I presented there, where you had a 10th map, you cannot do the same. All right, so if you do the calculations using the pointwise formula of the transfer operator, you can show, so I want to compute the Sobolev norm of the transfer operator. By direct calculations, just taking derivatives, basically, you get that this is smaller. I write this directly, L epsilon, and this is nice, 1 over T prime F prime plus L epsilon. Well, the bad guy appears. T double prime epsilon over T prime epsilon square. And this will be F, I guess. All right, so simple properties of transfer operators. They are weak contraction in L1. Okay, so I get directly 1 over T prime F prime plus T double prime over T prime square, and this is F. Okay, Well, the first one I want to contract. I want a contraction. I want a Soto-York inequality. And I have a piecewise expanding map. So this will be 1 over lambda, where lambda is my expansion factor, f prime 1. This is good news. But here, what I want to do, I want to avoid, well, what you usually do. You say, OK, I want to work with W11, with L1 being the weak norm. Well, with this, you run into problems, is that if you want to get the L1 norm of F, well, you have to take the L infinity of this guy, and this is not bounded. But if you look at this example, well, the L2 norm of this guy here is bounded, and this is the whole idea. It's just to use a P norm according to the singularity that you have, and this will do. Okay. And you get a Soto-York inequality. What do you do with W21? It's again the same idea. You take another derivative, you do the calculations, and you look at the order of the comparison between the third derivative and the order of the singularity, and you do the same stuff. You get, again, a Soto-York inequality on W21. And with some work, some topological conditions on the initial map, we can prove actually not only quasi-compactness, but spectral gaps in both spaces. All right, so stop here, and I'm happy to take questions.